The Curiosity rover captured this panorama after arriving at a region crisscrossed by hardened low ridges called boxwork patterns. Images like these and data collected on Mars are raising new questions about how the Martian surface was changing billions of years ago. The red planet once had rivers, lakes, and possibly an ocean, although scientists aren't sure why. Its water eventually dried up and the planet transformed into the chilly desert it is today. By the time this boxwork region formed, the long-lived lakes were gone in Gale Crater, but water was still percolating under the surface. The rover has found dramatic evidence of that groundwater when it encountered crisscrossing low ridges, some just a few inches tall, arranged in boxwork patterns. The bedrock below these ridges likely formed when groundwater trickling through the rock left behind minerals that accumulated in those cracks and fissures, hardening and becoming cement-like. Eons of sandblasting by Martian wind wore away the rock but not the minerals, revealing networks of resistant ridges within. The ridges Curiosity has seen so far look a bit like a crumbling curb. The boxwork patterns stretch across miles of a layer on Mount Sharp, a 5-kilometer-tall mountain whose foothills the rover has been climbing since 2014. Intriguingly, boxwork patterns haven't been spotted anywhere else on the mountain, either by Curiosity or orbiters passing overhead. When viewed from space, the boxwork patterns look a bit like spiderwebs, and a big mystery that has puzzled scientists is why the ridges were hardened into these big patterns and why only in this region. As Curiosity drives on, scientists will be studying the ridges and mineral cements to better understand how they formed. Important to the boxwork patterns, history is also the part of the mountain where they're found. Mount Sharp consists of multiple layers, each of which formed during different eras of ancient Martian climate. Curiosity essentially time travels as it ascends from the oldest to youngest layers, searching for signs of water and environments that could have supported ancient microbial life. The rover is currently exploring a layer with an abundance of salty minerals called magnesium sulfates, which form as water dries up. Their presence here suggests this layer emerged as the climate became drier. Remarkably, the boxwork patterns show that even in the midst of this drying, water was still present underground, creating changes seen today. While scientists hope to gain more insight into why the boxwork patterns formed here, Mars recently provided some unexpected clues. The bedrock between the boxwork ridges has a different composition than other layers of Mount Sharp. It also has lots of tiny fractures filled with white veins of calcium sulfate, another salty mineral left behind as groundwater trickles through rock cracks. Similar veins were plentiful on lower layers of the mountain, including one enriched with clays, but had not been spotted in the sulfate layer until now. Many impact craters on Mars were filled with ice in past climates. Sometimes this ice flows or slumps down the crater walls into the center and acquires concentric wrinkles as a result. This observation shows an example of this. There are other ways that scientists know the material in the crater is icy. Surface cracks that form polygonal shapes cover the material in the crater. They are easy to see in this springtime image because seasonal frost hides inside the cracks, outlining them in bright white. These cracks form because ice within the ground expands and contracts a lot as it warms and cools. Scientists can see similar cracks in icy areas of the Earth and other icy locations on Mars. If you look closely, you'll see small polygons inside larger ones. The small polygons are younger and the cracks shallower, while the large ones are outlined with cracks that penetrate more deeply. This observation shows Olympia Undi, a vast dune field in the North Polar region of Mars. The image was collected during the spring, that is why the dunes are still partially covered by the winter frosts. As the region heats up, the frost will dissipate to reveal the dark sand beneath. The density of dunes and the alignments of the dune crests varies with location, controlled by the amount of available sand and the predominant winds over time. Olympia Undi consists of a broad sand sea or erg that partly rings the North Polar Cap from about 120 degrees to 240 degrees east last longitude and 78 degrees to 83 degrees north latitude. The dune field covers an area of approximately 470,000 square kilometers, bigger than California but smaller than Texas. Olympia Undi is the largest continuous dune field on Mars. Olympia Undi is not the only dune field near the North Polar Cap, however. Several other smaller fields exist in the same latitude, but in other ranges of longitude, for example Below's Undi and Sitten Undi. The most common dune forms on Mars are Barkhan and transverse dune forms. In regions with limited available sand, individual Barkhan dunes will form, where the surface beneath and between the dunes is visible. In regions with large sand supplies, the sand sheet covers the underlying surface, and dune forms are found modifying the surface of the sand sheet. In this case, transverse dunes are more common. While Barkhan dunes point downwind, transverse dunes are more linear and form parallel to the wind direction. The square-shaped transverse dunes in Olympia Undi are due to two prevailing wind directions. NASA's Mars Odyssey orbiter used its Thermal Emission Imaging System, or THEMIS, to capture this view of Arsia Mons, an ancient volcano, while studying Mars's atmosphere, which appears here as a greenish haze above the scene. The Thermal Emission Imaging System captured the incredible image well before dawn on the red planet. The southernmost of the three Tharsis volcanoes, Arsia Mons, is 450 kilometers in diameter and almost 20 kilometers high. For comparison, the largest volcano on Earth is Mauna Loa, which measures 121 kilometers in diameter and roughly 9 kilometers high from its base on the seafloor. A large crater known as a caldera, produced by massive volcanic explosions and collapse, is located at the summit of all of the Tharsis volcanoes. At 120 kilometers wide, the Arsia Mons summit caldera is larger than many volcanoes on Earth. This type of image shows Mars's limb, the edge of the planet's horizon. By flipping on its side while in orbit, Odyssey can point THEMIS head-on at the limb and capture images of the Martian atmosphere. This unique view allows scientists to see the structure and shape of dust and water ice cloud layers and observe how they change over the course of seasons. Understanding Mars's clouds is particularly important for understanding Martian weather and how phenomena like dust storms occur. This is THEMIS's fourth limb observation since it began pursuing this new kind of science in 2023. When possible, the camera's team has tried to include an interesting surface feature, such as Olympus Mons, the tallest volcano in the solar system.